Yeah, but I'm glad this happened before, actually.
Okay, so is everybody there who has to be?
You probably should wait until Dr. Shaw gets here, right?
Yeah, okay, so we'll wait a second, yeah.
Yeah. He might have thought it was in the other room. Yeah, this is 101. Oh, yeah, we're supposed to. Yeah, okay. That's what I was thinking. Maybe Dr. Shaw, he probably went there, but he would then, because it does say have R1.
I know, it was not your fault, it's our fault.
No, I did the same thing. I did the same thing.
But you know, HC 101 is our home.
Yeah.
Pretty much, so it feels a little. Thank you, Linda.
Oh, you're welcome. I just thought we would wait until,
Oh, let's see.
what do you think?
I was actually telling us.
Yeah, as far as I know, yes.
So let's see, I was just saying that, I didn't realize it was an R1. 101. Are you talking?
Yeah.
No, we're fine now, so, yeah.
Even though I mentioned he would have went to the one and realized just like I did, because I forgot. And then he would have realized, oh.
Yeah, 101 has a big part of it.
Yes.
Some alumni.
Alumni.
Oh, is that what it is? Alumni.
Yeah, so it's a big spread, so whatever. But anyway, so, Chen is handling the lunch plan.
That's right.
Is he coming here to this
He
meeting?
didn't tell me that he was, I don't know.
How's he gonna start?
Good point. I mean, I'll check, I'll send him a message. See, we were messaging other, yesterday and.
You a visitor?
I retrained my.
Yeah, she is in our work. Oh, I had no idea.
We are not.
I don't know if you were a guest, but the speaker or what.
Heather Edwards.
Heather
Yes,
Edwards,
yeah.
yes.
The, Niels is part of our committee, our search committee. Damla is our chair of computer science, and Amrit is, he was on the committee.
Maximum
But he
public.
is an AI faculty member.
Huh? Yeah, that's
Yeah,
it.
yeah,
That's
the message.
I tell Jenny to put the room number and this Zoom link, so.
But because actually, Lisa, that's why I sent you a message.
Thank you, okay. Good. So, sit here.
Oh, I will make sure that he found it on here.
Okay. Okay, so I guess we are starting, right? Okay, so I don't know if you can hear me from here, but today's talk is going to be from Shashank Sonkar at Rice University. And the topic is going to be Pedagogy meets AI, Challenges and Innovations in LLM-Powered Learning. Please proceed, VR.
It's an honor to be here at UCF, and thank you, Professor, for such a kind welcome. Today, I'm going to talk about a topic that is very close to my heart, both as a researcher as well as an educator. How can we harness the potential of AI and specifically large language models to address some critical challenges in education? So I was talking to one of my collaborators, let's call her Katie for this conversation. She told me that every Sunday, like she's a high school teacher, and she told me that every Sunday she spent countless hours grading homeworks, planning lessons for the next week, and just trying to keep up with endless administrative tasks. She's happy with her job, but she's exhausted. And K-12 teachers are ranked the most burnt out profession in US. And when one of our colleagues retired last summer, the school really struggled to hire a replacement, and so are the other 86% of public schools. Higher academy isn't doing any better. They are going through an adjunctification crisis, and hence there's a dire need to support our educators and our burnt out teachers. Because when they are burnt out, the students will struggle. The national math and reading score hit a historic 20-year low in 2022. The SAT scores are dropping, and this means the kids are not ready to go to college. Around 60% of them need some sort of remedial coursework in math or English. One would hope things would look better at home, but at home things look even worse. Like 21% of US population is illiterate, half of them read below 6th grade level, and 34% struggle with basic primary math. And also, like with the looming threat of AI, there's an urgent need to urgently upskill and reskill this adult population as well. So a natural question will arise. Can you use AI to help our educators and our education system? The short answer is yes. The top levels of US agencies are actively engaged with this question. This is a recent bipartisan report which recommends empowering US educators and teachers with AI training and resources because they themselves are very concerned with stagnated K-12 math and reading scores. There was a recent, like 2 weeks back, an executive order which also recommends using AI for high impact tutoring and lifelong learning. There's also an acknowledgement and recognition of the potential and difficulty of using AI for personalized learning. Like personalized learning is a very powerful tool that can support a burnt out teachers as well as boost academic performance. And it has been recognized as one of the 14 grand challenges of the 21st century. And these challenges are really hard because they include like reverse engineering the brain or preventing nuclear terror. So what is personalized learning? For us to understand personalized learning, we need a backdrop of how traditional learning works. Typically, teachers teach, students do their homework, which gets graded eventually. There are few limitations with this cycle. Like irrespective of the student's background, their knowledge gap, prior knowledge, or misconceptions, all of them get the same set of reading material and the same set of problem sets. And the grading cycle is typically slow. It takes weeks and sometimes even takes days and sometimes even weeks. And by that time, the students have already moved on to the next topic. With this backdrop, we can understand what is personalized learning. It is all about creating adaptive learning systems that put the learner at the center of his or her educational journey. It can be through providing them customized instruction materials that are very specific to their knowledge gaps. It can be through providing them individualized instructions or just rapid feedback on assignments that appropriately challenge them. And AI is the key to making personalized learning a reality. Student modeling approaches such as deep knowledge tracing setups form the technological backbone of adaptive learning system. One can scale one-to-one individualized instruction with AI tutors and increase the frequency of assessment using automated assessment tools. My work has identified technical challenges in using AI for personalized learning. In the field of student modeling, we find AI and specifically large language models find it really hard to mimic student thinking patterns. They incorrect counterfactual complex chains of reasoning. And hence, it's a barrier to providing them high quality feedback. If you don't understand how your students are thinking, you will not understand like how to personalize your feedback to that particular student. In the field of using LLMs for tutoring in homework problems, we find LLMs tend to give away the solutions of homework problems to the students very quickly. And that is not at all optimal for learning because learning only happens when you actively engage with the question, which doesn't happen if LLM is giving away the solutions. And we found that current automated assessment tools don't really work well for long form responses. So we'll dig into each of these challenges one by one. We'll dig into cognitive student modeling, but let's understand a brief history of student modeling. We'll begin with traditional student modeling. The task of traditional student modeling is to predict whether a student will answer correctly or incorrectly when tested on a knowledge component. Knowledge component are concrete skills that the students need to master, and these setups like models are generally implemented through RNNs such as LSTMs. And the core limitation of traditional student modeling is the granularity at which it operates. It tries to predict student success or failure at a skill level. And in order to overcome this limitation, we asked the following key question back in 2022. How fine-grained can you go with the analysis of predicting student performance? Can you predict the student performance at the question level itself? It might seem like a naive implementation change in the code for TSM in which you just substitute knowledge component ID with question ID. But this naive implementation change leads to the issue of overfitting. And in order to overcome the challenge of overfitting, we adopt two standard ML practices. First is smart initialization of your question ID embeddings. We use the word-to-vec algorithm. Word-to-vec is a word embedding algorithm in NLP, which embeds words which have similar meaning in a vector space so that they're close to each other. And the reason why we use word-to-vec for initialization of question embeddings, because student assessment history is, after all, a sequence in which questions that have similar meaning occur together. And that is the whole driving principle of using word-to-vec, which is based on the distributional hypothesis NLP, in which like words that have similar context have similar meaning. The second standard practice is use a regularizer. We add this regularizer to a loss function, which makes sure that the success probabilities of questions belonging to a knowledge component are not too dissimilar. And with these two changes, you can get much better performance than the naive implementation of substituting your question like knowledge component ID with your question ID. Let's take a step back. So what I've shown you on is not just about initialization or regularization. It is about asking like how fine-grained can you go with predicting student performance?
So can you go back to the previous slide? So what is so you have some approach to do what? Like it will test student how much they have learned or something, or?
Yes. So in this instance, so let's say you have like E12, it can try to predict whether the student will answer it correctly or incorrectly. So let's say you have like testing systems like GRE or TOEFL, which are adaptive. So if they have high probability that the student won't answer the next question correctly, they don't generally give that particular question to the student. So that is the task of like question level student modeling, whether given a question, he will answer that exercise correctly or incorrectly.
So what is K1, K2, and what are these?
So even E2, E3 are exercises corresponding to a knowledge component, which is testing equality. So K2 is a knowledge component, which is
math equality, that's what you mean, right?
Yeah, math equality.
Plane vector probability, that's what you mean, right?
Yes.
And so it's testing these concepts, equality, inequality, and all this thing. And E1, E2, E3 are what?
Exercises, correct.
Exercise, I see.
Sequence of exercises chosen exactly carefully based on that student's weakness, is that right?
Yes. So like this is not adaptive. Like the task is like you are given like, let's say the sequence from 1 to 11 for a new exercise, whether like the student will answer that exercise correctly or incorrectly.
So you want to test student whether they have understood these concepts, and there's an adaptive test or something, right?
Yes.
So what exactly you have done? You have a new method to do that, and you're showing the table which does better or something. What's the big picture?
So the big picture is like generally people used to predict whether the student will answer like questions belonging to a knowledge component correctly or incorrectly. So like whether he will answer probability correctly or incorrectly.
Okay.
What my work has shown that like you can even take the analysis deeper. Like you can even predict like whether he will answer which exercise in this particular knowledge component correctly or incorrectly. Because these are broad skills, and like maybe he understands the base rule, but he doesn't understand other rules. So like it's all about understanding.
So that's what you've been able to do. And can you just quickly tell us how you did? Like what is the sequence?
What did you do? Like so you have large language model or something? Or?
So this is a very like 2020 paper. So like here we just use LSTMs in which we feed the exercise and we try to predict whether the student will answer it correctly or incorrectly. So you have to start like you have to make like initialize these question ID embeddings. So what we found that using word-to-vec initialization for these question ID embeddings is a good starting point for training these models.
Okay, so you train the LSTM, you train LSTM, right?
Yes.
So then to encode these question answer, you encode it using word2vec
Yes.
and compared to what? Like,
Compared to random vectors.
and you found that, can you show the table now?
Yes.
So then you're comparing this with, which is yours? Is that
The
okay?
last one.
Huh?
The last
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 column is yours?
Yes.
Okay, with fast text embedding and Laplacian regularization. Okay, so, and these are other two approaches are from where? Like, you published this paper in EDM or something? What's EDM?
Like educational data mining.
I see, okay. Okay, yeah, I think it'd be good if you, because you're going too fast, so we are not getting
I
what,
see.
just slow down and just explain. It's pretty interesting area.
So one question I do have though, word2vec lets you compare similar words, right? But you're looking for similar concepts in the question, is that right?
So we are looking for like word2vec is an algorithm which can cluster two words which have similar context
Yeah.
close to each other.
Yeah.
So generally, let's say like here you have like plain vectors, like so the questions that belong to plain vector generally occur with similar context, which is like inequality of probability. So like you can use the same intuition behind distributional property hypothesis, which drives the word2vec algorithm in order to embed this another kind of sequence. Because like a sentence, after all, is a sequence of words. So if the hypothesis is applying to this particular sequence, which is based like how meaning is attributed to IDs in the sequence, you can use the same logic to embed a new sequence.
But on top of that, you are training your LSTM with the additional regularizer term, right?
Yes.
So that's what gives you the better result, no?
So both of them give you the, so I haven't shown the ablation.
Okay.
So like,
okay.
I just wanted to make the pretty. So the regularization works like it makes sure that questions belonging to the same knowledge component have success probability which are not too dissimilar. Because you're not taking out the knowledge component information from your system now. So how do you integrate it back? We do this with this particular regularizer.
Okay, good.
So like the question that we like, it is about regularization and like initialization. But the deeper question is like, how fine-grained can you take the analysis of predicting student performance? So the ultimate goal is to predict students' actual responses. And that is the task of cognitive student modeling. So let me explain it through a story. Once there was a fish and a frog, both of them were very close friends, but frog decided to visit the land for a couple of years. And when frog comes back, fish asks, oh, what all did you see? So frog replies, oh, I saw birds, I saw humans, and I saw cows. And these are the mental images, what the fish imagines the birds to look like, the humans to look like, and the cows to look like. So you can see all of them have like some denominator of how the word of fish looks like with fins and like frogs. So humans are being imagined as frogs. So no matter how much correct information that you are imparting to a learner, it will always get distorted through the lens of prior knowledge, misconceptions, and knowledge gaps. And this brings us to a much more discrete way to understand cognitive student modeling. It's through the art of creating distractor or incorrect choices for multiple choice questions. So how exactly do instructors go about this process? So there are two key steps. So they, with their years of experience, they can predict common misconception pattern that students exhibit. Then for a new question, they can follow the reasoning behind these misconceptions to create distracted choices which can act as cognitive traps for students who exhibit such misconception. For example, what is 1 + 2 × 3 + 4? Instructors know some students tend to solve it from left to right and like ignore the BODMAS rule or the PEMDAS rule. So they will use 13 as a potential distractor for that particular student. Some students just apply addition before multiplication. And instructors can use 21 as a potential distractor for those students. And these two steps are the key to cognitive student modeling. Like, can you predict students' actual responses based on their past observations that you see? And why we are so interested in like personalized learning like cognitive student modeling because it unlocks personalized learning. It is the key to conditional distractor choice generation based on student past performance. And if you can create such distractor choices, basically you are in the head of the student. You can give him like specific knowledge intervention for his knowledge gaps. You can give him high quality feedback specific to that student's misconception. And you can use it for teacher training, adult workforce development as well. So like this is a recent like paper, like how would a Turing-like test for personalized education look like? How will you evaluate whether your AI understands student cognition at the level of human expert teacher? So the test is conducted in two phases. First, you collect data. So let's say you have Alice and Bob. Alice solves the equation left to right, and Bob solves it from applies addition before multiplication. In the phase two is where the real test kicks in for a new question. Can your AI predict whether Alice will answer 28 for this new question and Bob will answer 70? So humans also provide distractors, and by analyzing whether students select distractors generated by AI at rates similar to distractors generated by humans, you can understand how well your humans, like AI understands human cognition at the level of expert teachers. And like just like this question about personalization to education, like understanding how students think, it reveals something about personalization across domains. Like the key to any meaningful personalization is to understand how that human thinks, like their belief systems, their knowledge gaps, and their insecurities. And cognitive student modeling is a very specific instance of this universal AI challenge, which is developing theory of mind, which is understanding how humans think. And like education is a very good test bed because that is where the human thinking is most transparent. You will get your graded answer sheets for your assignments within 1 week or so. So, but the implications of this research extend far beyond a classroom. You can use it for developing customer service chatbots. Like if you are deploying a customer service chatbot, the chatbot must understand the misconception that users have for that particular service or tool. And with all this, like education providing us a rich test bed of like how students think, let's ask this question: can current language models act as effective cognitive student models? It's an interesting tale of three research questions. The first one is, can LLMs mimic student thinking patterns? If not, like as a data scientist, you will throw student data at it and see if data fixes your problem. We find it doesn't really fix the problem, and you need specialized fine-tuning measures to make LLMs as robust cognitive student models. These are the three research papers of mine, which go into each of these questions one by one. We'll go into start with MalAlgo QA. MalAlgo QA is a very unique data set. Generally, question answering data set consists of answers and like questions and their answers. What we did with MalAlgo QA is also to augment these choices with student rationales. So for instance, in the last example, we were using what is 1 plus 2 cross 3. For the distractor choice of 13, we also have the corresponding distractor. Like the student ideally solved it from left to right to arrive at this distractor choice. Mal-algorithm is a term that was coined by us. Basically, it reflects conceptual misunderstanding that students have, which they follow to reach these incorrect conclusions. There's an example on the right from the data set. So let's say you have a square, each side is 3 inches long. If you add 3 inches to each side, how many times does the area get bigger?
Slow down, because see to make it meaningful, you're going too fast, nobody's getting it. So just slow down. Maybe you don't have to cover everything, right?
Okay.
If you want to enjoy what's your work. So let's understand what you're saying here. So here you have a question, when you add 3 inches on this thing, you give this to what? LLM? You give this to LLM, or
So
what's your contribution? Yeah.
So the task is a contribution. So let's say you are given a question, you are given a set of 4 rationale and an answer choice. Can the LLM tell which of those rationale is leading to that?
Yeah, I understand. Okay, so there's question and there's multiple choices, right?
There's only one multiple choice, but we have 4 rationale corresponding to each of these.
4 rationals.
So these are the 4 rationale. Like
So you give this question to the LLM?
yes.
and you ask it, when you add 3 inches to each side of this and of this thing, so then how many times bigger does the area get? Yes? And then you are saying which of the 4 rational would lead to answer 22. Okay, good. So the answer is 2. Correct answer is 2.
Correct answer is like
What is the correct answer?
3,
3.
4, like 27.
So this is
yeah.
just a wrong.
Yes, the correct answer is
confusing
4.
LLM.
Yeah.
Yeah, go back. So you're confusing LLM, say, well, what, how it will come up with 2 and what will be rational.
Yes.
Right? So that's the idea. And these are the 3 rationals.
Yes.
You give it to it and it selects one.
Yes. So
Okay.
it's shown A, B, C, D, and it has to select A in this. This
Okay,
instance.
the new side is twice the original side. There must be twice 2.
So this rationale is a little bit like grounding?
Yes.
So you are trying to say these are like the chain of thoughts in
Yeah, chain of
some
thought,
sense,
yeah.
like the thought
Yeah.
that LLM would lead to that answer. And
Yes.
those are the multiple choice in the thought process of the LLM that would lead to the answer.
Yes.
Correct? Yes. Okay.
So this one, so you're saying, so this is the correct rationale, which says answer is 2 or 3, what does it mean? So the area must be twice 2. What does twice 2 means? You said 2 is not correct, right?
Yeah. So the student who answered 2, this is the likely thinking that he did to arrive at this answer.
Okay,
So it doesn't do like proper like.
I see, okay. So the idea is that, well, you're not looking for the right answer, but you got the answer and you want us LLM to give, how did the student arrive that answer?
Yeah.
And this rationale.
Yes.
I see. And this is the task, like you have solved, like you have done research to do this or something, or?
Yeah. So with this paper, we first showed that this is a decode reasoning task. That will lead to any AI, like if an AI solves it, it will mean like we have achieved personalized
It'll be
AI.
good for,
Yeah.
yeah.
So
Okay.
this is the first task that we show to the community.
And how
And-
successful? I'm just curious now. So just jump far ahead. So
Yeah.
were you like lost in doing it or were you quite successful?
We have had a bit of success, but not total success. Like it turns out to be a very hard reasoning task.
Could you explain these things?
Yes, yes. Because like generally LLMs are trained on correct data and they know the right chain of thought behind the correct answer. But this task is very fundamental to personalization in education. Right.
So you showed that LLM cannot do that or something, or what was the conclusion of your paper?
So my conclusion was like state of the art LLMs are like when it comes to identifying the right algorithm, they are like 95-96% accurate, but when it comes to finding the rationale behind the distracted choice, they are only like 60-70% accurate.
Okay.
So there's a huge gap.
Yeah.
That
They give you the right answer, but they may not tell you the rationale, the reasoning, how.
No, they don't know the rationale of getting the wrong answer.
Huh? Yeah, wrong answer.
Yes.
So but what you are saying, 95% of the time they are what?
they are able to tell the right. So they're like for the correct choice, you have to identify the right algorithm.
Yeah.
So they are able to identify the right algorithm behind the right choice because that's the kind of data they are shown. But when it comes to identifying the algorithm behind the incorrect choice, they are not that good.
Incorrect choice.
Yeah.
And what do you mean by algorithm? Like what are the kind of algorithms?
So these rationales are like written in form of algorithm.
Yeah,
Oh,
the
I
kid is
see.
using some algorithm they had.
Yeah, okay. Okay, so this, so there's a benchmark which
We created this
you
benchmark.
created, okay.
Yeah.
So that's your contribution, and you evaluated these different LLM, GPT-4, Llama, and so, right?
Yes.
Okay, so that's your contribution.
Yes.
Yeah, so I think it'd be good that you explain the problem, slow down, you don't have to finish everything.
Yeah. Okay. Yeah. I'll take.
And
Yeah.
I know when I was young like that, I want to cover everything,
Yeah.
that's not a good idea, no?
Okay.
One other question then. So did you have a way to make a suggestion some of the LLMs could do this better or not?
So, like, I can go into that paper which show that initial success in having these two contradictory algorithms embedded in the same LLM.
Is that like your next paper or something?
Yes.
Okay.
So-
Okay, then I will stop you.
But that saying this algorithm, is that a correct phrase to use? Like,
No, I mean, it's rational or.
yeah,
I don't know,
it's
what the
like
kid
a-
thinks.
yeah,
It's whatever the kid thinks, right?
Yeah,
exactly,
Regardless
it's
of
like a
what you want.
different.
What
So
the kid thinks.
the rationale behind me using the word algorithm is
Yeah.
to separate ourselves from like the community using the word misconception. So misconceptions are vague, like they can be random slips of error,
Yeah.
but these are systematic patterns. So let's say like in this case, like this equation, like what is 1 + 2 × 3? So if the student is solving it from left to right, that's an algorithm. So if you are given a new question,
Yeah, yeah.
You will also do that, same thing.
Yeah, yeah,
to
same
that
thing,
And
like-
give the wrong
Yeah, yeah,
answer.
maybe the right, maybe don't call it algorithm, because algorithm is too late, right?
Yeah,
Why do you
that's
call it
right.
kid algorithm?
so
or
we
kid
call it
concept?
mal algorithm. So mal algorithms means
Mal-
But
mal-
then
mal-
it's messy, right? So this
So-
is in the student set, that is the pseudocode he is writing to
yes,
solve
yes,
those
yes.
questions. So if you can identify that pseudocode that is creating this wrong answer, you can
Yeah.
have a
Fix it.
personalized
Okay.
Fix it.
yes.
way to teach that student.
Okay, so the real objective over here is whatever problem you're testing the student on, you need to find what sort of partly logical method a kid might use to come up with all possible answers for that. And then you feed that to the LLM, and that tells you how the kid is thinking.
Yes, that's what we want
So
the,
that's a difficult problem, because as the problem gets, you're asking, this is like a quantum computing problem. What are all the different ways that you could get a wrong answer? Because the LLM only knows the right answer.
yeah, so there, like, we, in the AI paper, that was a theoretical paper in which we showed that, like there are like common studies in ed-sci literature which show that like small number of misconceptions cover a lot of student population. Without that concentration inequality, like you can't like do such kind of, like, that will be too ambitious. So even in my research, like, we focus on those few misconceptions only, like to cover like 80% of the like student base. But for 20%, as you mentioned, it's like, I'm not sure, like, maybe my
That's
kids
a tough
will go.
problem
Yeah,
to come up with those questions.
yeah, so.
Okay, very good. So now we understand.
Yeah. So let's skip, like, so let's come to that paper in which we actually try to induce such kind of
Fix the problem.
fix the problem. So we first write a way to create such kind of synthetic data at scale. So we made this library mal-algo-py. It's a computer algebra system library that can solve your equations under certain misconceptions. So for example, you are given a distributional property misconception in which you distribute the term only to the first term inside the parentheses. So the B only gets multiplied to C and not to D. And these are like, I'll tell you, like, these are the common cognitive science misconception that students exhibit. And these are universal across countries. So this library can solve this particular equation, 10x = 2 times 3x + 1, under the distributional property error, and give you the solution x = 1 divided by 4, which is the answer student would have got had they had this particular misconception. So with this library, you can create a lot of synthetic data at scale and understand what is happening in large language models, because they are data hungry and you need to have a way to create such data at scale. So how we build mal-algo-py, we went with 14 algebraic problem types, all equations with single unknown. And from like different cognitive science studies, we figured out 20 mal-algorithms applicable to these algebraic equations. And with this, you can create this data set at scale.
No, but let me just be clear. So you are playing the role of identifying the mal-algorithm. You the design, you the professor.
Yes.
Saying, not getting the system to learn how to develop its own mal.
So with this, you can understand whether you can firstly teach LLM to have both the algorithms inside.
Yeah, I understand.
Yeah. So that is the first.
First
yeah.
steps first, you think.
Yeah. So let's have certain metrics. So one is your overall correct accuracy. Like, so in the process of learning these mal algorithms, you do not want your LLM to start forgetting how to solve problems correctly. And then for a misconception M, you ideally want your LLM to solve this problem MP following the logic behind that particular misconception. So with this, you can concretely define what a cognitive student model is. It should satisfy two key properties. One, it should have, for a misconception M, it should have high misconception accuracy. And then it should also have high correct accuracy on problem types to which M doesn't apply. This is because misconceptions often coexist with correct knowledge, And there will exist certain few students who have distributional property error, but they can still solve problems correctly which do not have parentheses. So with this, like, you know what you are looking for. And now let's start instruction tuning LLMs as CSM. So first you train a base model to solve all problems correctly with high accuracy. And then in order to mimic a misconception M, we start to gradually introduce these misconception examples. So as you can see from the chart, like as you increase the misconception examples, LLMs start to mimic the pattern behind these misconceptions. And like, it's after all pattern which LLMs will be good at. But they start to forget how to solve problems correctly. And that is the real issue. So MAL-ALGO-PY allows us to investigate what are the problem types that it is becoming bad at. Are those the problem types to which M applies or doesn't apply?
So which LLM is this?
These are, I think this is for Llama 70B. And
so you get similar thing for different LLMs, or you just have done for one LLM?
So we did it for just for Llama 70B. So like, because each point is a new model that we train. And like,
okay, good.
So like, what the question now is, like, as you can see from the blue line, LLMs start to forget to solve problems correctly to which that misconception applies. That is all right. Like, okay, like I'm asking it to like make a mistake in questions which have parentheses. It's okay to get those problems incorrect.
So in this one, you just take the pre-trained LLM, you don't nothing. You are just testing, right? You are not fine tuning or anything.
Oh, these are all fine tuned. So
You
So the
fine-
second step.
Yes.
First step.
What?
this is all fine. So like here, like
So you take the Llama 70 billion and then you fine tune with your data set or something?
yes. So with MAL-ALGO-PY, we can create a lot of data by
Okay.
different instantiation of A, B, C, D, and
Okay.
application. And as you increase the number of samples in your training data set,
Mhm.
you can get the LLM to mimic these misconceptions.
I see. So when you fine tune the LLM, so this data set, this is your data set, you generated your own?
Yes.
Okay, and so what is you give question and then you have the wrong or correct answer and you want to update the LLM using that? right?
Yes. So like the instruction was the prompt was
Yeah.
on which it gets fine tuned. This is the question. This is the misconception. Apply this particular misconception on this particular question. Then we give it like one example to show what that misconception implies. So this is the question, this is the whole prompt. And for this question, generate me a proof tree and get me the question answer the student will have got had he applied this particular misconception on this particular question.
So there's a lot going, right? But you train, but you do not talk about that.
So,
So how you did that?
yeah.
So you took the LLM and you have this data set, your misconception on that, and your prompt, and then you're asking LLM to give you the tree or something, or what were you saying?
Just give me the like tree, but we extract the final answer.
Okay, and what is the tree?
So here is the example of a tree. So here, like, let's say
Mhm.
10 students, and I ask you to apply this particular rule
Mhm.
for this particular question.
Yeah,
Give me x equal to 1 divided by. And during fine tuning, we show it the entire steps. It's
Okay.
not like this library can
Okay.
generate all these steps.
okay, so let's say you find it with that, right? Now, what plot you are showing, that's during testing after fine tuning,
Yes,
and so that's the different data set?
yes, that's a held out data set. So like you can create A, B, C, D. So
Mhm.
you can know like which ABCDs are in your training set and which are in your test set.
Yeah, so that's, okay, continue.
Yeah, so as you can see, like once you start mimicking the misconception, the LLM forget to solve problems correctly. So the question is like, which questions is it forgetting to solve correctly? So it forgets to solve problems correctly to which like this particular misconception applies. Let's say it is applying to equations with parentheses. But it also starts forgetting to solve problems correctly to which it doesn't apply that misconception. The drop is not much, but it is still significant. And this is the general trend student data. So like they start, like if I'm training them on to be like mimicking a good tutor on biology, they start forgetting how to solve problems in chemistry correctly.
So the big picture you have here, that you intentionally you're kind of attacking LLM, that it should do misconception or something, and then you're testing how well that it does and how it impacts the other. What's the big, what exactly you're trying to do?
So the big picture, it should be able to solve questions correctly with misconception, because that is the key to creating
Solve correctly.
as well as incorrectly.
Incorrectly,
Yes.
right? So you want LLM typically would solve correctly.
Yes.
Right? So then you want to bias it, that you give a misconception, and that means to solve incorrectly.
Yes.
Yes?
Yes.
And so this fine tuning is about that.
Yes.
And then you're testing that did it do that? And it is doing it.
Yes.
But then the problem is that other concepts, which you did not ask it to do misconception, it is impacted. That's the idea, right?
Yes.
It's a big picture. Yeah, so I think it'd be good to keep it that level, right? Because everybody is using LLM and so on, but you are not really, conveying this message.
Okay, yeah, I'll try to.
Yeah. Okay, so then this is another, so this is like an attack, you are attacking the LLM and you're making it that should do the wrong thing. And then you're saying, well, I take for this thing, but then you are unintentionally you are taking other things also.
Yes.
Okay, good. Yeah,
Yeah.
thank you.
So yeah, so if we are on the same topic, like, so the attack is happening because the knowledge that you are trying to encode conflicts with the knowledge that is already encoded in your base language model. The issue, like why we can't encode a lot of misconceptions at once, is because these misconceptions are also contradictory to each other. So like, let's say you have one possible distributional property error, but there might exist another distributional property error which conflicts with this rule. So you train it on M8, but if you want to learn another rule, you'll start forgetting M8. So that is the whole rationale, like how do you go about such fine tuning? So the trick we found was like you need to strategically mix right amount of correct samples with your misconception examples, and how it translates into NLP is like, let's say you're training it on a lot of biology student data, and you have one chapter from your textbook. You need to paraphrase it a lot of times to hit that right number of correct samples. And if you do that particular, hit that right number of correct training samples, you can achieve both these two properties at the same time.
So to start with, like, why this misconception is such a big deal? Because, you want to, use LLM for the right thing.
Yeah.
It's working. So why is that? Why do you want to take it?
So you want to have a way to get figuring out what the kid is doing wrong.
You want to understand.
Yeah. So, and also like it's for personalization in across domains. So let's say if I want to create a customer service bot for Xfinity Wi-Fi. So let's say like I need to train it to understand the misconception of that customer service industry, or like I am from advertisement industry for 4 years. And if I need to give you the right advertisement for you to click on, I should understand like your thought processes, your belief system, like if you are price conscious or you are very earth sustainability conscious, because advertisement like is where the money comes from the internet. So this is the challenge to personalize across domains. Like you need to have contradictory information in the same model, and you should be able to get that behavior once you write that particular behavior in your prompt. Like solve this question under this wrong assumption.
So the reason that other concepts are also going, down, it's very similar to the visual language model, right? You use the, you take the LLM and then you put an image encoder, train it with that, there's capability of vision also. But then people have found out that text performance goes down.
Yeah, yeah,
Very similar.
yeah,
right?
yeah.
Okay.
So,
Yeah.
catastrophic forgetting,
Yeah.
like I think.
Mhm.
Yeah.
Okay.
So this is all the, like, I'm extending this work, like, so, like, just to wrap up this type of project, like, this was one of the, like, problems that I introduced to the educational NLP community. It is gaining a lot of traction. There was a recent $50,000 Kaggle challenge, which was hosted by one of our collaborators in UK, and with whom we first identified this particular issue. And we have posed distracted generation as the key reasoning task behind any personalized AI for education. People thought like question generation is a solved art now that we have large language models. What I've shown you all and hopefully convinced that creating those distracted choices which are plausible to each student based on their misconception is still a very hard task for these language models. So with this, we can come up to my next topic, which is how do you go about using LLMs for tutoring?
So from these, you have two remaining things, right?
Yeah.
So you have only 15 minutes left. So which one do you think, because you won't be able to talk about both.
So I'll go with this one.
This one?
Yeah.
Okay.
So there's a huge opportunity of using LLMs for tutoring. Like that's a place where teachers are not there. And like with the data I've shown you all, like it's a dire situation out here. So, and we tried using LLMs for tutoring, but we found that LLMs aren't really aligned to be used as homework tutors. They're definitely aligned to be helpful, harmless, and honest, but it's to a general internet user. Like when we make a query to our favorite language model, we expect to get a good high quality answer. But when we are using LLMs for homework tutoring, we expect the LLMs not to give away the solution of the problems to the student too soon. Like try to help them with hints and feedback. And prompt engineering doesn't work. We tried this, like we got a lot of prompts curated by various subject matter experts to elicit such desired scaffolding like behavior. But even with a model as powerful as the Llama 70B or Quen 72 billion model, we couldn't get such a behavior. Like it was very random, like 50% of the times. So let's look at some data. So the first instance, any student makes a mistake, the next response from a large language model should ideally be a hint, not a feedback. So let's say you have two responses, one corresponding to a hint, one corresponding to a solution. You can measure the likelihood of both these responses. And in NLP, you measure it through perplexity. Perplexity and likelihood are inversely proportional. And here you can see the perplexity of hint and solution are roughly similar. And this aligns with our observation that LLMs tend to give away the solution 50% of the time. So let's understand the goal of what we are trying to do here, the goal of pedagogical alignment, which is to increase the likelihood of the hint and decrease the likelihood of the solution. The arrows are reversed because we are measuring perplexity, and perplexity and likelihood are inversely relational. So you can use supervised fine-tuning algorithms to accomplish this objective. You can further optimize using policy optimization algorithms like DPO, KTO to further improve these models. But where does the training data set come from? The student-tutor conversations are not present on the internet, and even if they are not of very high quality. And that is where my class and class plus plus framework comes in. So the class is the key to creating synthetic data sets for your supervised fine-tuning algorithm, and class plus plus is the key to creating synthetic data sets for your policy optimization algorithm. So class consists of two GPT-4 generated data sets, but importantly, both of them are subject matter expert validated, and secondly, seeded by high quality OpenStax data. The scaffolding dataset teaches the LLM how to plan the conversation. How do you decompose a problem into sub-problems? And the conversational dataset is basically a tutor walking the student step by step through regular hints and feedback. So once you have these two datasets, you can fine-tune any large language model of your choice. But how do you know how good it is performing? So, and that is where the key challenge comes in. Like, because new language models drop in every day, and if you are again and again going to your subject matter expert after every fine-tuning, it's a very resource consuming process. And that is where the thought fields come in. So before the tutor bot responds to the student, we always generate 3 thought fields. One is the evaluation of the student response. The second is the action that you should take based on this evaluation. And third is the sub-problem state. These are the categories corresponding to each of these 3 thought fields. After sitting with subject matter expert for like few months, we were able to like map out the entire state action space of your tutorbot model in a mutually exclusive and exhaustive manner. The reason we went through this effort, because this allows us a lot of functionalities. First, it allows us to use and get feedback from your subject matter expert in a very systematic manner. So pedagogical alignment is not just about not giving him, the student, the hints. It's about, and the solution. It's about stepping in with the solution at the right time. And like with this systematic manner, you can get feedback from your teachers whether the LLM is kicking in with the solution at the right time or not. And once you have this gold data set, you can evaluate any large language model of your choice once you fine tune it on the training data set. And so like, let's say you have new models, like a recent like DeepSeek model, you can fine tune and see how good it is behaving. But it was not possible if you did not have such a systematic design to collect data from your subject matter experts. And third is like a preference data set curation, which led to class plus framework in the last cycle of EMNLP. So it consists of 3 agents. One is a GPT to student model that talks to a GPT tutor model and an SFT tutor model. And in case any of these 2 tutor models disagree on any of the evaluation field, you can create it as a preference pair. And you need preference pair to run any of your policy optimization algorithm. So let's say you use SFT algorithm using the class plus framework. You can further optimize your SFT models using any of your policy optimization algorithm with this preference data set.
So what is KTO and what is IPO?
So these are like, one is direct proxy optimization identity. These are different policies.
I mean, I know DPO, but I never heard about KTO. What is KTO? Amrit, do you know a KTO? Yeah, what is KTO, IPO? These are similar to these?
Yeah, so like KTO removes the dependency. So DPO needs a thumbs up and a thumbs down.
Yeah,
like
winner and loser.
Yeah, so for the same response. With KTO, it does away with this particular requirement. So for a particular response, either you need a thumbs up or a thumbs down.
Oh, okay.
So, and that's very useful. So generally, when like the
So again, I think it'd be good to give a big picture here, right? So you generated this data from the, how do you generate this data from the expert, you said, or this to do this fine tuning with DPO, for example?
So we generated this data, like first cycle was class plus class framework. So given a question, like we generate the data set using GPT-4.
GPT-4, okay.
And then we got it validated on these 3 thought fields.
3 what?
Like these are the, so before tutorbot replies, it outputs these 3 thought fields.
Thought field.
One is the evaluation of the student response,
Okay.
whether it is correct or incorrect.
Yeah.
The action that you should take, whether you should give him the hint or the solution.
Yeah.
And third is the sub-problem state, like which of the
So
problems.
these you got from GPT.
Yes, and got it validated by subject matter experts.
So the person, and what is subject matter, teacher? Or
Yeah, teachers.
Okay.
So,
And, yeah, go ahead.
Dr. Shah, this KTO is this Kahneman.
Kahneman, the slow
Yeah,
and fast. Huh?
Tversky optimization. So
Oh, I see.
Kahneman is this Israeli-American scientist that
Huh?
we were talking about.
The guy who passed away, Nobel Prize winner, right?
Yeah. David Kahneman, Daniel Kahneman.
Israeli guy, yeah,
Yeah.
okay. So, yeah, good, so, so this is interesting. So you are saying you get those 3 things and then you go to that expert and that's like round truth. And then you do the DPO on the top using that.
So we do SFT on top of
SFT.
that. Yes, supervised fine tuning.
Okay, so you are not doing DPO.
Yeah,
also.
so DPO needs a preference data set.
That's
Yeah.
what you don't you do the SFT,
Yeah.
right? So let's go to table now. So what you were showing.
So here,
Mhm.
like these numbers are like the percentages of like how many times it's getting that particular thought field correctly or incorrectly. So like the first one is evaluation of the student response. Second is action, like 61% of the times it's correct to predict whether it should give the hint or the solution. So these are the three fields that we generate and like define the categories for each of these three fields in a mutually exclusive manner so that it becomes a classification problem rather than multi-level classification. And once you have this data, you can fine-tune your language model, and for each tutorbot response, you can get these three classes.
So what does this, like you have some numbers which are higher in blue, right?
Yes,
What does that mean? DPO is better than SFT or something? Or-
yes.
But you said you did SFT, you didn't do DPO.
So we did DPO with the class plus plus framework.
Oh, I see, okay.
So class plus plus framework creates
Mhm.
three agents, and these three agents talk to each other, and you can create preference data set for them. So the big picture is like currently we are using it for like a math tutor in like Worcester Polytechnic. So the first class plus first class framework gives you a good enough model to deploy it in a classroom setting.
Okay.
But you need another framework which tells you how do you take this thumbs up and thumbs down data set to keep improving your model.
Yeah. Okay.
So class is like, I give you a good student like tutor model that
Mhm.
doesn't behave too badly with students.
Yeah.
But the class plus first tells you how do you keep improving this model based on the feedback that you are getting.
Yeah, okay, so for this paper, I mean, it's good, you've got this paper accepted in very top venue, right? So just briefly, what is the problem you solve and why your solution is great? Just 2-3 sentences. What's the problem you solve in this paper?
First, creating synthetic data set in a very systematic manner for a particular domain.
Okay,
The key is like, how do you make all these categories corresponding to each of the thought fields? It can differ from like customer service agent versus
okay, good. So
education.
you generated synthetic data.
Yeah.
Then you use the synthetic data set to do this fine tuning with these different methods.
Yes.
And then which one are the best?
Like KTO works the best actually.
Okay, good. I think that kind of thing helps because, people need to understand the big picture.
Yeah, yeah.
Okay,
Okay,
okay, good. Yeah,
Yeah.
so you have, I think 3 minutes left now.
okay.
You have some concluding slides or something or?
Oh, like,
Yeah.
yeah, I can go. This is
Yeah,
just.
go to the last few slides.
So last few slides is like how I'm planning to extend my work on cognitive modeling. So I showed you one of like the works on like math misconceptions.
Mhm.
So like I was a visiting scholar to ETH last fall, and this is the
Okay, Julie?
yes.
Okay,
So
which department? Computer
yes,
science?
yes,
Oh, I see. They're doing this kind of work?
yeah. So the lab is pretty much similar, like NLP for education, like so,
So those are NLP guys? or-
yeah, those are core NLP guys.
Oh, okay,
So
good.
like
Yeah. Mhm.
here we generate like how, so we saw like misconceptions happening in mathematical, like math domain, but how does it transfer to natural language? And this can, for this we used their math word problem solver. So it can generate proof traces for solving math word problems. But here also like students exhibit common misconception when deciphering the language of your math word problem. For example, keyword strategy is like whenever they see fewer, they always do subtraction, but it is not always correct. So I'm extending this work with ETH Zurich still, and just a recap that this is for personalization across domains.
Yeah.
And
So are you meeting with Dr. Carmaker? Like, because he's very big in theory of mind. I think you should talk to him.
yes,
He has a faculty.
okay.
Santu Carmaker. Okay, good, yeah, so.
And this is a new project, like we had an idea because there's an existing attention span crisis in education, like nobody wants to read lengthy textbooks. So how to solve this problem is to like flip the script, like make it more problem-based learning. like generally students learn better when like research has shown in some domains. And with this, like it creates to a challenging AI/ML problem. One is it incorporates my work on knowledge graph completion. Uh, so there's a curriculum planner that operates over this knowledge graph, which makes sure that students learn all the concepts by the end of their educational journey. With LLMs, you can create personalized text lessons, and with multimodal uh, models, you can create like accompanying short videos, which, yeah. And like this is the last slide, like I'm also part of new my advisors NSF infrastructure. Like it allows researchers to conduct large scale educational studies which can inform innovation in teaching and learning. And we are developing like privacy preserving and NLP techniques to preserve the privacy of student data. And with this, yeah, I complete my. Thank you.
I think you have a parameter meeting this afternoon.
Yeah.
Yes, over
Yeah,
Zoom.
so I think should do that.
Zoom meeting, either Zoom.
Okay. Very good. Yeah, so I think, you guys have next lecture.
Yeah, and I'm meeting with you on it.
Okay, okay, good, yeah, thank you.
I'll even do that one.
Yeah.
So you just want to lunch. Yeah, yeah, yeah. So, I can